Hello everyone. Today we will going to see some practice questions from the chapter Coordination Compounds. This is part 4. Let's start. Disclaimer which says the images used in our slide deck are for education purposes only. We respect the intellectual property rights of original creators and owners of these images. If you are the owner of any images used in this deck and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the images. This is our index slides. We will going to see the practice questions from question number 25 to question number 32. Let's start with the question number 25. The magnetic moment of the complex anion chromium NO NH3 Cn whole 4 2 negative is. We have given a complex here of chromium and we have to find out the magnetic moment for this complex anion because it is having a negative charge. Options are 5.91 bm, 3.87 bm, 1.73 bm or 2.82 bm. You have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. So the correct answer is option C, that is 1.73 bm. So in this complex chromium NONH3 cyanide whole 2 negative, let's suppose that the oxidation state of chromium be X. So what we have to find out? We have to find out the orbital configuration for the chromium atom. For that, we have to first of all find out the oxidation state for the chromium in this particular complex. So let's suppose the oxidation state of chromium in this complex is X. So we will count it as chromium is having X oxidation state, NO is having +1 oxidation state, ammonia is having 0 oxidation state, cyanide is having -1 oxidation state, times 4 because 4 is the total number of ligands present as a cyanide in this complex. And it is equals to the total charge present on this complex anion, which is -2. Now we just solve this equation for X value. It will be X minus 3 is equals to -2 or X is equals to +1. Right? X equals to +1 means the chromium is having +1 charge on it, and for that the configuration, the noble gas configuration will be argon 3d5 4s0. Okay, the chromium configuration is argon 3d5 4s1, but as it is having +1 charge, so it will donate 1 electron, and it then the configuration will become argon 3d5 4s0. And if you write in the orbital terms, it will be this. This is the 3d orbital, and 5 electrons should be filled in this, so it will be like this, not any paired electron. But as you know that cyanide, that is Cn negative, and NO, which is present in the given complex, they both are strong field ligands. Okay, cyanide and NO are strong field ligands, and due to the presence of strong field ligands in the complex, the unpaired electrons will pair up of Cr positive. So these unpaired electrons will get paired up and it will become like this after the pairing. So this 2 will pair up, this 2 will pair up, and this one remain as it is as unpaired electron, right? So you can see it will be, there is one unpaired electron. Now N value will become equal to 1. N is the number of unpaired electron present in the orbital. So N will become equal to 1 because there is one unpaired electron. So therefore we use the magnetic moment formula, which is mu is equals to under root n times n plus 2. N is 1, we just put the value 1 times 1 plus 2, that is 3. 3 times 1 will be 3. So under root 3 is having a value in decimal is 1.73 bm is the unit for the magnetic moment. So this is the final magnetic moment we are calculating for the chromium positive ion for in this complex, and thus our C option is the correct answer. Okay, let's move on to the next question. Question number 26. In which of the following complexes the crystal field splitting will be least? Crystal field splitting energy will be least in which of the complexes? That means which is the lowest? Options is iron H2O whole 6 3 negative, chromium NH3 whole 6 3 positive, cobalt C2O4 whole thrice 3 negative, nickel CO whole 4. So from these complexes, which one is having the least crystal field splitting? We have to tell the complex. You have 10 seconds. Think about this question. After that, we will see the answer. Okay, let's see. The correct answer is option A, that is iron H2O whole 6 3 negative. Del naught. Del naught is basically crystal field splitting energy. So del naught depends on the strength of negative field ligand. So the ligand we have, what is the strength of that ligand? The crystal field splitting will depend on that. So spectrochemically, it has been found that the strength of splitting is as follows for the different ligands. This is a spectrochemical series according to which we arrange the different ligands according to their strengths. Highest strength is for carbonyl, then cyanide, then NO2, then ethylene diamine, then NH3, then pyridine, then NCS, then H2, then O2 negative, then oxalate 2 negative, then OH negative, then F negative, chlorine negative, SCN negative, S2 negative, bromine negative, and iodine negative. Least strength is for iodine negative ligand. So according to, we use this concept, spectrochemical series, and in the options, one option is cobalt, oxalate whole thrice, whole 3 negative, right? You can see that oxalate is having the lowest strength, right? But it behave as a strong field ligand here in the cobalt oxalate whole thrice 3 negative complex. Therefore, this is the only one rare example where it is strong field ligand. Other than that, it is behaving, it will behave as a weak field ligand. And other than oxalate, only H2O will remain as a weak field ligand among the given options, among the given other ligands in the options. So it will have del naught value least. Okay, so after looking on the options given, we have two least strength ligands, which is oxalate and water, right? But oxalate in this complex is behaving, it is a rare example where it is behaving as a strong field ligand. That's why FeH2 whole 6 3 whole 3 negative is answer, because H2O is a ligand which is having the del naught value least according to the spectrochemical series, and thus option A is the correct answer. Okay, let's move on to the next question. Question number 27. In which of the following octahedral complex species the magnitude of del naught will be maximum? Now we have to find out that from these octahedral complexes, which complex has del naught value maximum? Options are cobalt H2O whole 6 2 positive, cobalt cyanide whole 6 3 negative, cobalt oxalate whole thrice 3 negative, or cobalt ammonia whole 6 3 positive. You have 10 seconds to think about this question. After that, we will see the answer. Okay, let's see. The correct answer is option B, that is cobalt Cn whole 6 3 negative. So del naught magnitude depends upon the charge of central metal atom. So splitting or crystal field splitting energy magnitude depends upon the charge of central metal atom in the complex and the strength of the ligand in the complex. So among the given options we have Cyanide is the strongest field ligand as per the spectrochemical series. So the complex having this cyanide as a ligand, that is cobalt CN(CH3 negative), will exhibit the maximum value of del naught, because del naught value and the crystal field, del naught value and the strength of the ligand is directly related. And as per the spectrochemical series, cyanide is the strongest field ligand. That means the complex having cyanide as a ligand will be having the maximum value of del naught. Thus, our B option is the correct answer. Moving on to the next question. Question number 28. Among the ligands ammonia, ethylene diamine, cyanide, and carbonyl, the correct order of their increasing field strength is. Options are most for cyanide, then ethylene diamine, then ammonia, then carbonyl. Most for carbonyl, then cyanide, then ethylene diamine, then ammonia. Most for ethylene diamine, then carbonyl, then ammonia, then cyanide. Or most for carbonyl, then ammonia, then cyanide, then ethylene diamine. You have 10 seconds to think about this question. After that, we will see the answer. Okay, let's see the answer. The correct answer is option B, that is most for carbonyl, then cyanide, then ethylene diamine, then ammonia. So we used here the spectrochemical series concept, that based on the spectrochemical series, ligands arranged in increasing order of crystal field strength of theirs. So for the given ligands we have in the question, the strength order or the ligands increasing field strength order is this: most for the carbonyl, then cyanide, then ethylene diamine, and then least for the ammonia among these four given ligands. And thus B option is the correct answer. Let's move on to the next question. Question number 29. The color of the coordination compounds depend on the crystal field splitting. What will be the correct order of absorption of wavelength of light in the visible region for the complexes cobalt cyanide (CH3 negative), cobalt ammonia (CH3 positive), and cobalt water (CH3 positive? You have to tell the order of wavelength of absorbed light in the visible region for these three complexes given. Options are most for cobalt cyanide (CH3 negative), then cobalt ammonia (CH3 positive), then cobalt water (CH3 positive). Most for cobalt ammonia (CH3 positive), then cobalt water (CH3 positive), then cobalt cyanide (CH3 negative). Most for cobalt water (CH3 positive), then cobalt ammonia (CH3 positive), then cobalt cyanide (CH3 negative). Or most for cobalt cyanide (CH3 negative), then cobalt ammonia (CH3 positive), then cobalt H2 (CH3 positive). So you have 10 seconds to think about this question. After that, we will see the answer. Okay, let's see. The correct answer is option C, that is most for cobalt water (CH3 positive), then for cobalt ammonia (CH3 positive), and then least for cobalt cyanide (CH3 negative). So basically, the CFSE, crystal field splitting energy. CFSE means crystal field splitting energy of ligands is in the order this: highest for cyanide, then for ammonia, then for water. And we use the concept of a crystal relationship between the crystal field splitting energy and wavelength of absorbed light here. So basically, the crystal field splitting energy of ligands are inversely related to the wavelength of absorbed light in the visible region by the complexes. Therefore, if you know the crystal field splitting energy order of various ligands, you can just reverse that order and you can have the wavelength of absorbed light order, right? So therefore, wavelengths of absorbed light will be in the opposite order, as highest for the cobalt H2 whole 6 3 positive, then for cobalt ammonia whole 6 3 positive, and then least for cobalt cyanide whole 6 3 negative. Right? So we just reverse the order of crystal field splitting energy of ligands, and we get our wavelength order of absorbed light for the given three complexes. And thus, C option, having the correct order, is the correct answer. Okay, moving on to the next question. Question number 30. Which of the following compounds is not yellow colored? So, options are zinc whole twice, iron cyanide whole twice, K3 cobalt NO2 whole 6, ammonia whole thrice, osmium MO3 O10 whole 4, or barium chromium O4. You have 10 seconds to think about this question. After that, we will see the answer. Okay, let's see. The correct answer is option A, that is zinc whole twice, iron cyanide whole twice. So, zinc whole twice, iron Cn whole 6, potassium whole thrice, cobalt NO2 whole 6, and ammonia whole thrice, osmium MO3 O10 whole 4 show color due to DD transition. Okay, so these three complexes show color due to DD transition, while BaCrO4 is colored due to charge transfer phenomena. So these are two phenomena due to which the complexes shows colors. Okay. Further, according to the spectrochemical series, the strong ligand possessing complex has higher energy and hence lower wavelength. We just talk about it, that if the energy is higher for a complex or for a ligand, then its wavelength or the complex having that particular ligand wavelength will be lower, right? Because they are inversely related, energy and wavelength. So the strong ligand possessing complex has a higher energy and hence lower wavelength. Therefore, complex containing NO2, NH4 positive and O2 negative ligands show yellow color, while cyanide negative force the complex to impart white color. So we can get the idea of the colors by using the wavelength concept for the different colors we know. Okay, and thus zinc whole twice, iron cyanide whole twice is a complex having a color not yellow. Okay, it is not yellow in color, and thus A option is the correct answer. Moving on to the next question, question number 31. The octahedral complex of a metal ion M3 positive with 4 monodentate ligands L1, L2, L3 and L4 absorb wavelength in the region of red, green, yellow and blue respectively. The increasing order of ligand strength of 4 ligands is, we have given the color of the wavelengths absorbed by the 4 ligands L1, L2, L3, L4 attached to the metal ion M is. It will be red, green, yellow and blue respectively. We have to tell the increasing order of ligand strength for these 4 ligands. Options are most for L1, then L2, then L3, then L4. Most for L4, then L2, then L3, then L1. Most for L1, then L4, then L2, then L3, or most for L3, then L4, then L2, then L1. You have 10 seconds to think about this question. After that, we will see the answer. So the correct answer is option B, that is most for L4, then L2, then L3, then L1. So ligand field strength is directly related to the energy of the light absorbed, and the energy of the light absorbed is inversely related to the wavelength of light absorbed. So wavelength and energy are inversely related, right? So if you see that L1 is absorbing the red wavelength light, L2 is absorbing the green wavelength light, L3 yellow and L4 blue. And if you see the wavelength order for these different colors lights, it will be the wavelength for the red light will be highest and the wavelength for the blue light will be lowest, right? So red, yellow, green, blue. we arrange it as per the Vibgyor, right? So therefore, lesser is the wavelength of light absorbed, greater the extent of crystal field splitting energy, and hence higher is the field strength of the ligand. So we can arrange the order of the ligand strength as L4 highest, then L2, then L3, then L1. L4 is associated with blue color, and blue color is having the lowest wavelength, so it will be having the highest field strength. And L1 is associated with the red absorbed wavelength, so and red is having the wavelength highest, so the field strength for the L1 will be lowest. So this is the correct order, and this B option is the correct answer. Moving on to the next question, question number 32. According to the EAN rule, how many carbonyl groups should be attached to iron? EAN is effective atomic number. Options are 4, 5, 6 or 8. You have 10 seconds to think about this question. After that, we will see the answer. Okay, let's see. The correct answer is option B, that is 5. So, according to the EAN rule, EAN is equals to atomic number plus oxidation state of the metal plus 2 times N, where N is the number of ligand attached and the atomic number of iron is 26, we know, and the atomic number of next noble gas, if you look upon the noble gas configuration for the iron, so the iron is having argon as the noble gas configuration. So argon is having the 18, I guess, the atomic number, but the next noble gas atomic number will be 36, right? So EAN will become 36 because we need here the larger atomic number or EAN value. So 36 will be equal to 26 atomic number plus oxidation state of metal, as we have not given the complex, so we just suppose the iron is having 0 oxidation state as no charge is present, so 0 plus 2 times N. Solve it for N, you will get 10 is equals to 2N and N is equals to 5. And N is number of ligands attached. So therefore, number of carbonyl groups attached to iron is equals to 5. And thus our B option is the correct answer. Thank you.